All right, so the last section we dealt with strong acids and strong bases and how we can rather easily determine the pH. Now that we get into the vast majority of acids and bases, we need to be aware of how we deal with equilibrium equations and equilibrium calculations. So this is a totally different beast, and there's one more thing that we're going to talk about in this that we could have talked about in the last one, but I decided to wait till now so you can see why we go through that. So weak acids means that it's going to be double arrow reactions, which means equilibrium is going to be involved. So if you take a weak acid, which we'll call HA, which is aqueous, it's not going to break down 100% in water, so we use the double arrow. And this is going to be H positive aqueous plus A negative aqueous. And because of that, we're going to have the K. And the K for this is going to be the concentration of hydrogen times the concentration of I negative all over the concentration of the weak acid. And because this is dealing with acids, we use a lowercase a for that Ka, which means the ionization value for a weak acid. Now I'm going to be using this basic formula for all the acids because there's always going to be a positive part, which is H, and a negative part, which is whatever's left over, negative charge. I could sit there and show you how to come up with all those negative ions. You understand that if you just remove a hydrogen, it's going to be that, which we're going to do in the first problem. But this is the format I'm going to be using from now on. If you don't use it, that's fine. To me, it's just simpler to use this basic idea here, as you'll see. So, in your book, you need to turn pages to page 761, and we're going to look at some odd number problems there. We'll start with number 27. Now, number 27, what they want you to do is just simply draw or write a reaction showing the ionization of each particular acid. In the case of number 25, now here I'm not going to use the H and the A. I will for the problems after this, but they want to see what you were writing down for positive and negative ions, and I am too, so this is going to be important. HOCN is an aqueous substance. It's a weak acid, so it has to be dissolved in water. Any acid has to be dissolved in water, but because it's weak, we use a double arrow. And so the positive component is always going to be H. Then everything else left over is going to be a negative ion. It's that simple in writing these down. Now, having written that down, I'm going to tell you a fact about my life that you will not believe. But I have a granddaughter whose name is OCN. Literally, the letters OCN. How do you pronounce your name, OCN? OCN. Thank you. For the next, that's part A. And the next one I'm going to look at is part D. This is, they write this, I don't like inorganic chemists, and I'm pretty much guarantee that inorganic chemists wrote this textbook. They put HCO2H. I'm going to write it out because that's how you write out formic acid. If you write it down the other way, that's fine. But the reason why I do it this way is because it emphasizes which is the acidic hydrogen. Remember, the acidic hydrogen is the hydrogen that is bonding to the oxygen. It's the one that comes off semi-freely. It's not completely freely. But this is the acidic hydrogen right here. Not here. That's bonding to carbon. There is no difference in, well, there's a very tiny difference in electronegativity between hydrogen and carbon. But there's a great deal of difference here, and that's why this hydrogen comes off. So double arrow, because this week, this is not one of the 7 I gave you. And this will give you H positive because of that. And then this is your negative ion. Okay? So So that's what they're looking for there for those types of problems, which you will be doing. The next one we're going to look at is that was number 25, not 27. The next one is number 27, and this is more of what this chapter is all about, is looking at weak acids and how they don't really break down completely and how you can predict what the pH is. Now, with a strong acid, you just look at the concentration, hit the negative log of that, and boom, you got your pH for that acid. Not the case here for a weak acid. So, let's take a look at this. You're given this gobbledygook here. I'm just going to say aqueous breaks down into H positive aqueous and A negative aqueous. Now, you could have written the whole spiel out here. HC3H3O2 yields H positive plus C3H3O2. Don't need to. But here's the deal of this. This is where it gets kind of important. They say for this that the pH is 2.63. And they want to know what is the value of the Ka. Okay, well the Ka is going to be the concentration of hydrogen, a hydrogen ion. And by the way, they call this hydronium ion, even in the previous problem. Let me explain very quickly what that means. H positive is hydrogen ion. You add water to that, it will bond a little bit to that to create H3O. That is technically hydronium ion. And you will never, ever, ever see me write hydronium ion down in a reaction, because it is the same thing as H positive. And since pH is figured out on H positive, and technically not really hydronium, because by the name pH, I would use the H positive. If they ask for hydronium, you want to put H3O positive down, fine. H positive is what I'm sticking with here. So that's what we're going to be dealing with here. Now, again, we're going to go to this general form for all weak acids, A negative over concentration of HA. And they don't know what the Ka for that is. They do give you the pH, and here is the one thing we did not talk about, and that is how you can go from pH to H positive concentration. So let's refresh our memories as to what pH means. What does the P in pH mean? It means negative log. And what does the H mean? It means H positive. Hey, look, it's not hydronium. Gee, what a surprise. Now, if I want to find the H positive, this is like any other algebra problem. If you want to find something, you have to go backwards in the problem to find out what it is. Like if you have 3x plus 4, you have to subtract 4 and then add 3, where normally you would do the multiplication first and the addition subtraction next. In algebra, you go backwards. So it's addition subtraction first, multiplication division last. Same thing here. Since this means negative log of H positive equals some value, well, we know that the base for this is 10. And I'm going to rewrite this in what we call exponential form. So this is going to be equal to negative log means negative exponent of 10. So the 10 to the negative, and the exponent here, logarithm or exponent, is pH. So negative pH, and that equals, sorry, that should not be an equal sign there, that should be an arrow showing a step. 10 to the negative pH equals the concentration of hydrogen. So if I want to get the concentration of hydrogen in this equation, then I'm going to have to take 10 to the negative pH, which is 2.63. Type that into my calculator, get 10 caret negative 2.63, and we get 2.34 times 10 to the negative third moles per liter. That is that value right there. Now, remember, when these reactions dissolve, you start with original concentration, you lose a little x here, you gain x here, you gain x here. That's our generic form for the ice thing that we do. Okay? So, what we don't know is the original concentration, and that's what we're trying to find out. Well, so we go through and oh, they do give us the Ka. I'm sorry, the Ka is not missing here, so that's a little weird. The Ka is given to us here as 5 point. Oh, this is what we want. What I didn't have written down is that the original concentration is a 0.10 mole. That's kind of important information. Okay, so, but since H positive is X, then that means that this is equal to X. So I can put an X here, this number goes in for X here, this number goes in for X here, and this number goes in for X right here. So 0.10 minus X. And that will give me my Ka. So let's do that. So we have X times X on top, that's X squared. So this is going to be 2.34, I'll put Ka over here, times 10 to the negative third quantity squared over, and then in the denominator is 0.10 minus 2.34 times 10 to the negative third. Do that, and you get an answer of 5.61 times 10 to the negative fifth. And Ka has no label. That's all we can do with it. So the big thing here is changing the pH to an H concentration. Now in the previous lesson we had the pH concentration. We changed that to pH. Here we're doing just the opposite. So it's the 10 to the negative pH is going to be equal to your hydrogen ion concentration. Keep that in mind. That is a big, big thing to know. Next one, problem number 31. We're skipping 29, going right to 31. We're given here, again, another compound, PADA they call it. I'll call it A, HA, and A negative. It doesn't make any difference. But what we are given here is the Ka. So let's do this thing here. H, A, aqueous, H positive aqueous, plus A negative aqueous. And Ka for this is equal to H positive concentration times A negative concentration over the concentration HA. And they do give us the value for this in this problem, which is 2.2 times 10 to the negative fifth. And the other piece of information they give us is that the original concentration of HA is 0.05 molar. And the question they want to know here is, what is the concentration of hydrogen when this is done, and what is the percent